Hello, this is Kalyan. Today in this lecture, we will discuss about the three-phase AC circuit analysis. So, the type of the alternating currents and voltages discussed so far are termed as the single-phase currents and voltages, as they consist of a single alternating current and voltage waves. The single-phase systems involving single-phase currents and voltages are quite satisfactory for the domestic applications. Even the motors employed in the domestic applications are mostly the single phase. For example, the motors used in mixers, coolers, fans, air conditioner, refrigerator, these are the single phase induction motors. But however, the single phase system has its own limitations and therefore it has been replaced by the polyphase system. For supplying the power to the electrical furnaces, we need two-phase systems. Similarly, the six-phase system is usually employed for the power electronics control system. For general supply, generally the three-phase system is universally used, that is, for generation, transmission, and distribution of the electrical power. The three-phase system has been universally adopted. And the applications of the two-phase supply and the six-phase supplies, they can be obtained from the three-phase supply. The polyphase system means the system which consists of numerous windings or circuits. The poly means the numerous or the multiple, and the phase means the windings or a circuit. A polyphase system is essentially a combination of several single-phase voltages having same magnitude and frequency, but they should be displaced from one another by equal angle, which depends upon the number of phases and can be determined from the following relations, where the electrical displacement is calculated as 360 degree by number of phases. So for example, if we want to use a three-phase system, then for a three-phase system, the electrical displacement should be equal to 360 degree upon 3, that is 120 degree. It means the three voltages of same magnitude and frequency, but their phase displacement should be 120 degree from each other. Three-phase systems can be balanced or unbalanced. So let's see the definition of the balanced and unbalanced system. A supply system is said to be the balanced when several voltages of same frequency and have same magnitude, equal magnitude, and they are displaced from one another by equal time angle. For example, for a three-phase system, as we have discussed that the phase displacement should be 120 degree apart from each other. So in this case, the supply system will be considered as a balanced system. Remember one thing, the three-phase circuit can be categorized in two parts. One is the supply system and another is a load part. So a supply system is said to be the balanced when several voltages, for example, if we want to consider the three-phase supply system, then three voltages of same frequency and having equal magnitude, and they should be displaced from one another by 120-degree phase angle. So a three-phase three wires or three-phase four wire supply system will be balanced when the line-to-line voltage are equal in magnitude and displaced in phase by 120 degree with respect to each other. This concept we will discuss later in this lecture. Further, in a four-wire system, the voltage with respect to the neutral of the three-phase wires should be equal to one another in magnitude, and they should be displaced in phase by 120 degree with respect to each other. On the other hand, three-phase supply system will be considered as the unbalanced when either of the three-phase voltages is unequal in magnitude or the phase angle between three phases is not equal to 120 degree. Then this supply system will be considered as the unbalanced. But in our discussion, we will consider the balanced system only. Similarly, the load side, if we want to consider a balanced load, then a load circuit will be considered as a balanced when the impedance in each phase are same in magnitude as well as in phase. That means the impedance of the three phases will be exactly equal in terms of resistance and reactance. So the magnitude will be same as well as their phase difference will also be same. Any three-phase load in which the impedance in one or more phases differ from the impedance of the other phases, it is considered as an unbalanced three-phase system. Now, what are the merits of the polyphase system over the single-phase system? Because till now we have discussed about the single-phase system, but now here we have to consider the three-phase system, or in general we can consider it as a polyphase system. So let's see the merits and demerits. So the first point is, in a single phase circuit, the power delivered is pulsating in nature. It is okay for the lighting and the small motors that can be used in domestic applications. But with the large motors, it causes excessive vibrations. Whereas in polyphase system, the total power delivered is always constant if the load are balanced. But there may be any phase, the power of any phase may be negative, but overall the three phase power will be always constant with respect to the time. So therefore the polyphase system is preferred for the power loads or the high rated machines. Now, what is the pulsating power? So the voltage waveform is a sinusoidal waveform with respect to the time, and for a purely resistive circuit the current waveform is also same. So here it is the voltage and here it is the current. So if we want to find the power waveform, then the product of voltage and current will give us the power. So we'll get this type of waveform for the power. Here we can see that the waveform of the power is continuously fluctuating. The magnitude of the power is continuously fluctuating. This type of power is considered as a pulsating. The pulsating power can be used for the light loads and the small motors. But if we use the single phase pulsating power to the heavy motors, then due to excessive vibrations, there may be some mechanical damages. The next advantage is the rating of a given machine increases with the increase in the number of phases. For example, the output of a three-phase motor is 1.5 times the output of a single-phase motor of same size. Let's say we have two different uh, motors. One is of three-phase and another is of single-phase. So it can be seen that the if the size of the two machines are exactly identical, that means their length, width, volume, etc., then the rating of the three-phase machine is 1.5 times more than the rating of the single-phase motor. The next point is the single-phase induction motors have no starting torque. So we have to provide some auxiliary means to start the motor. For example, in our household applications, in the fan, we can see that there is a condenser connected in the fan. So this condenser here is basically used to provide the starting torque. Whereas if we consider the three-phase motors, there are different type of three-phase motors like synchronous motors, induction motors. Generally, induction motors are the self-starting machine. That means there we need not to use the condenser or any other means to start the motor. Whereas the synchronous motor is not the self-starting, so we have to use some prime movers to start the synchronous motors. But in industry, generally the induction motors are mostly used. Therefore, it is again the advantage compared to the single phase motors. The next point is the power factor of a single phase motor is lower than that of a polyphase motor of the same rating. We have already discussed about the power factor and we have seen that if the power factor is high, it is tends to 1, then it is better. So it can be seen that of same rating, the power factor of a single phase motor is lower than that of a three phase motors. So definitely the efficiency of the three phase motor is also higher than the single phase motors. The losses are less and so on. The three phase system requires 3/4 weight of the copper that is required by the single phase system to transmit the same amount of power at a given voltage and over a given distance. That means we have seen the transmission line. The power is transmitted from one place to another place through this transmission line. If we use the single phase system to transmit the power, then the requirement of the copper conductor will be more compared to the three phase systems. That means if we use the three phase systems, then the weight of the copper will be only the 3/4 of the weight of the copper that will be required for the single phase system. The next advantage of the three phase system is that the rotating magnetic field can be set up by the polyphase current through the stationary coils. This rotating magnetic field is basically used to run the three phase machines. When we will discuss a different type of three phase machine, there we will discuss this rotating magnetic field. And the rotating magnetic field can be produced only by the polyphase currents. If we use a single phase current, then the magnetic field that will be produced is considered as a pulsating magnetic field. Whereas using the three phase current or using the two phase currents, the magnetic field that will be produced, it will be rotating in nature. The polyphase system is more capable and reliable than the single phase system. As you have already seen that there are the losses are less, the efficiency are more, the power factor is better, as well as the three phase system is also reliable compared to the single phase system. Next advantage is the parallel operation of the polyphase alternator is simple as compared to that of the single phase alternators because of the pulsating reaction in the single phase alternator. The parallel operation means when two different alternators are joined together, then if they run simultaneously, this is considered as the parallel operation of the alternators. And if we want to connect the two alternators, then it is very much required to maintain their frequency, maintain their phases. So this is easily done in case of three-phase alternators. But if you want to do the parallel operation for the single-phase machines, then it will be little bit of difficult. However, the three-phase operations is not as practical for the domestic applications, where the motors are usually very small. It is as small as 1 kilowatt, and where the lighting circuits supply most of the load. As we have seen that for the domestic application, the voltage is 230 volt and 50 hertz. And in our household applications, the different type of motors are used in different appliances, and the ratings of the motor is only 1 or 2 kilowatt. So if we use the three phase power supply to run this small amount of power, then it will not be so much economical. That's why for domestic applications, for household applications, only single phase supply is used. Although the power that we'll get by the single phase supply, it will be pulsating in nature, but still it will be okay because the rating of the motors or rating of the other appliances are very small. Now, commonly used polyphase systems, although there are several polyphase systems such as two phase, three phase, six phases, but the three phase system is adopted universally because of its advantages over all other polyphase systems. If we use more than three phases, then it increases the complexity as well as the cost of the transmission and the utilization. We can use the six phase, but for that the complexity of the system will be increased as well as the cost of the transmission as well as the utilization will also be increased. So the knowledge of the three phase power system is therefore very essential for understanding the power technology. Fortunately, the basic circuit analysis technique that is used in solving the single phase circuits are directly applicable to the three phase circuits. Because the three phase circuits are identical and one phase represents the behavior of all of the above. Basically, a three phase system can be considered as the three phase system can be considered as the combination of three single phase system. So all the calculations and all the characteristics of the single phase system can be easily applied in a three phase system, in a balanced three phase system. Next, It's a generation of the three-phase EMF. How the three-phase EMFs are generated. We have already seen in single-phase AC power supply. In a magnetic field, suppose we have a magnetic field where the north pole and south poles are placed, and there is a coil that is placed between this magnetic field, and if the coil makes to rotate in anti-clockwise direction within the magnetic field, then we have seen that the EMF will be induced in the coil sides. This concept we have already seen in the single phase AC supply system. And we have already seen that the EMF that will be induced here, it can be mentioned as E is equal to E max sine omega t, where the value of E max, that is the maximum induced EMF, it depends upon the three factors, that is the number of turn, the angular velocity, and the value of the maximum flux that cut the conductor. And as these three values are constant, therefore the magnitude of the maximum voltage is also constant. And we have already seen that the omega is equal to 2 pi f, where f is the frequency. So this is the concept of generation of single phase voltage. One coil is placed within the magnetic field. Therefore, if we want to create three phase EMF, that means we have to use three different coils. So the system is like that. Three different coils are joined together and they are placed in a common magnetic field. The three coils should be identical. That means their number of turns, the conductor used, their dimensions, they should be identical. And if these three coils make to rotate with a constant speed within a constant magnetic field, then three EMF will be induced in three different coils. This is the concept of the three-phase EMF. So let's see the concept. When three coils joined together and 120-degree apart rotate about the same axis in a uniform magnetic field, then the induced EMF in each of them will have a phase difference of 120 degree. So let's see this figure. Here we have used a constant magnetic field, uniform magnetic field, and three different coils, that is A1, A2 is one coil, B1, B2 is another coil, and C1, C2 is the third coil. Remember one thing here, A1, B1 and C1, these are the starting point of the coil, whereas A2, B2 and C2 are the end points of the coil. And the first coil, that is A1, A2 is considered as the first coil. So the second coil is started after 120 degree. That means the angle between A1 and B1 is 120 degree. Similarly, the starting of the third coil is 120 degree from the second coil. And similarly, it should be 240 degree from the first coil. So if we place these three coils in this manner, that means their angle between two coils is exactly 120 degree. And these three coils are rotating within a constant magnetic field, and the rotation will be in anti-clockwise direction with the same velocity, that is omega radian per second. So three identical coils that we have already discussed, A1, A2, B1, B2 and C1, C2, mounted on the same axis, but displaced from each other by 120 degree, and they are rotating in anti-clockwise direction in a bipolar magnetic field, in a uniform bipolar magnetic field. A1, B1 and C1 are the starting terminals, whereas A2, B2 and C2 are the end terminal or the finish terminals. So in this case, if these three coils are rotating, then the EMF will be induced in three coils. So the EMF that will be induced in the first coil, it is represented by this red waveform, because the position of the first coil is along the x-axis. So at the position, it can be considered as a 0 degree. Then the induced EMF will also be 0 degree. Now as the coil starts to rotate, so the EMF will be induced, that we have already seen in the uh, single phase AC voltage EMF equations. Whereas as the three coils are rotating in anti-clockwise direction, that means the B is 120 degree beyond the before the after the coil A. That means after 0 degree after 120 degree, the voltage of the coil B will start to induce. So the voltage of the B coil started here. It is represented by the yellow curve. So this is the induced EMF of the coil B. Whereas the coil C is again 120 degree after the coil B. So the EMF induced in the coil B is here, and after 120 degree the EMF will be started to induced in the coil C. So if we plot the waveform of the three waveforms, three induced EMFs, then it can be represented by the red, yellow and the blue lines, where A is the induced EMF in the coil A, yellow is the induced EMF in the coil B, and blue is the induced EMF in the coil C. Here we can see that the phase difference between A and B is 120 degree. Similarly, the phase difference between B and C is also 120 degree, and similarly between C and A it is again 240 degree, 120 degree, or we can say that the phase difference between the red and the blue, that means the coil A and the coil C, is 240 degree. So when the coil A1 A2 is in position AB, that means along the x-axis, the induced EMF in the coil is 0 and it is increasing in the positive direction. The coil B is 120 degree behind the coil A1 A2. So the EMF induced in this coil is approaching its maximum negative value, and the coil C1 C2 is 240 degree behind the coil A1 A2. So as the EMF is induced in the coil has passed its positive maximum value and is decreasing. That means here at omega t equal to 0, the EMF in coil A starts to induce. In that case, the EMF in the coil B is negative. Here it has been shown the EMF induced in the coil B is negative. And the EMF induced in the coil C is just reaches the maximum and it is in the positive side, but it is in the decreasing order. So if we want to plot the voltages of these three coils, it can be shown here. The EMF induced in the coil A is represented by this red line. So it is A1, A2, that is the coil A. The coil B is 120 degree lagging the first coil. That means the EMF induced in the coil B will be 120 degree lagging the EMF induced in the coil A. And similarly, the EMF induced in the coil C will be lagging the EMF induced in the coil B. again by 120 degree. Remember one thing here, the phasors are rotating in anti-clockwise direction. So this is the rotation of the three voltages. So again, we have shown the waveform of the three-phase voltages. Since each coil being identical has an equal number of turns and is wound with the wire of the same type and same cross section, the induced EMF in each of the coil are of the same magnitude. The induced EMF in each coil is also the same frequency and same sinusoidal waveform, but they are displaced from each other by 120 degree. As we have already seen that the magnitude of the maximum induced EMF depends upon three factors, that is the number of turn, the angular velocity, and the maximum value of the flux. So here the three coils are identical. That means the N is same for three coils. These three coils are rotating with the same velocity, that is the omega radian per second. And the coils are placed in a common magnetic field. So the phi max is also same for each of the coils. Therefore, the magnitude of the maximum EMF that would be induced in each coil, it will also be same. But as the position of the three coils are 120 degree apart from each other, therefore the phase difference between the voltages will also be 120 degree. So again we can see the phasor diagram of the three voltages. A1, A2, the voltage in A1, A2 can be represented as E of A1, A2. The EMF induced in the coil B can be written as E of B1, B2, and the EMF induced in the coil C can be written as E of C1, C2. So the instantaneous value of the EMF that are induced in the coil A1, A2, B1, B2 and C1, C2, they can be given as the EMF induced in the first coil, that is E of A1, A2, and it will be E max sin omega t. Similarly, the EMF induced in the second coil, that is B1, B2, this is the instantaneous EMF induced in the second coil, and it will be again E max sin omega t minus 120 degree, because the EMF in the second coil is lagging by 120 degree from the EMF induced in the first coil. And similarly, the EMF induced in the third coil, that is C1 and C2, it can be represented as E max sin omega t minus 240 degree, because the EMF induced in the third coil is lagging by 240 degree from the first EMF. Now here we have seen that the EMFs are represented by as E A1 A2, E B1 B2 or E C1 C2. This is considered as the double subscription notation. So let's see what is the double subscription notation. Here the two letters are placed at the foot of the symbol of for voltage or currents, and the order in which the subscripts are written indicates the direction in which the voltage acts or the current flows. For example, if a voltage in a circuit acts in such a direction as to cause a current to flow from A to B, the positive direction of the voltage is from A to B, and the voltage may be represented as VAB or EAB. So here in this figure you can see that this is point A and this is point B, and the current is flowing from A to B. That means definitely the A is in higher potential and B is in lower potential. Therefore, the voltage potential difference between A and B can be represented as V of A and B. So it means it is the difference of VA and VB. Remember one thing here, the A is considered as a higher potential or the positive potential, and the second point is considered as the negative potential. So this is the concept of the double subscription notation. If the voltage is indicated by VBA or EBA, it means that the point B is positive with respect to point A, and the voltage causes the current to flow from B to A. That is, VBA or EBA indicates that the voltage or EMF act in a direction opposite to that in which VAB or EAB acts. So we can say VBA is equal to minus VAB. That means if we write here VBA, that means we have considered the B is the higher potential and A is the lower potential. But actually the current is flowing from A to B. That means definitely the A is in higher potential and B is in lower potential. So the VBA is nothing but the negative of VAB. Similarly, IAB indicates the current is flowing from A to B, but IBA indicates the current is flowing in the direction from B to A. Therefore, IBA can be written as minus of IAB. In this figure, we can see that the direction of the current is from A to B. But suppose if we want to mention the current is IBA. IBA means the current should flow from B to A. But actually the current is flowing from A to B. So the IBA can be considered as the negative of IAB. So this is the concept of the double subscription notation. Next concept is phase sequence. The phase sequence is the order or the sequence in which the current or voltages in different phases attain their maximum values, one after another. As we have already seen in this figure that when these three coils rotates in anticlockwise direction within a common magnetic field, the EMF induced in coil A will start from 0, and after 120 degree the EMF induced in the B coil will start from the 0, and again after 120 degree the EMF induced in coil C will start from the 0. Here the three coils A1 A2 B1 B2 and C1 C2 rotating in anticlockwise direction. Since the coil B1 B2 is 120 degree behind the coil A1 A2 and coil C1 C2 is 240 degree behind the coil A1 A2, therefore the first coil A1 A2 attain the maximum value of the induced EMF. The coil B1 B2 attain the maximum value of the induced EMF when the coil rotates further 180 degree. And similarly, the coil C1 C2 attain the maximum value after 240 degree from the first position. Since the induced EMF in three coils A1 A2 B1 B2 and C1 C2 attain the maximum value in order A, B and C. So the phase sequence here is considered as A, B, C. From this waveform, we can see that if we start from the 0 at omega t equal to 0, if we start, then we can see that the EMF in coil A attain the maximum value first. After 120 degree, the EMF induced in the coil B will attain the maximum value. And again after 120 degree, the EMF in coil C will attain the maximum value. That means the A will attain the maximum value first, then B and then C. So in this case, the phase sequence is considered as A, B, C. First A, then B and then C. Now, if the direction of the rotation of the coil is reversed, that means if these three coils make to rotate in clockwise direction, so in that case, the maximum value of coil A will attain first, then the maximum value of the induced EMF for coil C will attain, and then for coil B. Therefore, in this case, the phase sequence will be considered as A, then C, and then B. So, if these three coils rotate in anti-clockwise direction, then the phase sequence will be A, B, and C. And if the coils are rotating in clockwise direction, then the phase sequence will be A, C, and B. Now the interconnection of the three phases. As each coil of the three phases has two terminals, and if individual phases are connected to a separate load circuit, then we get a non-interlinked three-phase 6-wire systems. So let's see the figure here. So A1, A2 is the first coil, B1, B2 is the second coil, and C1, C2 is the third coil. If the three-phase supply system, this is the supply system, or you can say the generator side, and this is the load side. Now, if we not interconnect the three coils, then if we want to supply the three-phase power supply to the load, then we have to connect each phase of the load separately to the each phase of the generator. So A1, A2 of the generator side will be connected to A1 dash, A2 dash of the load side. Similarly, B1, B2 of the generator side will be connected to B1 dash and B2 dash of the load side, and similarly for C. So this system is considered as a three-phase 6-wire system. In such a system, each circuit will require two conductors. That is definitely we can see from this figure. For first coil, we require two conductors. This is conductor 1 and this is conductor 2. So overall 6 conductors are required to give the power supply. Hence, such system will be very complicated as well as the expensive. So in practice, a non-interlinked three-phase 6-wire system is not employed, but the phases are interconnected to give a three-phase 3-wire or three-phase 4-wire system. That means we have to interconnect the three coils. So there are two different type of methods to connect the three coils. So first one is called the star connected system, and second one is called the delta connected system. So let's see the figure. In first case, this is the coil A, B and C. Let's say these are the starting points. So it is A1, it is B1 and this is C1. Similarly, it is A2, B2 and C2. So the star connection will be obtained when we interconnect three similar terminals of three coils. For example, here we have connected three endpoints of the coils, that is A2, B2 and C2. So it can be seen like this. So A, B or C are the three coils. The common terminals are joined together and this is considered as a neutral terminal. Whereas the other terminals are connected to the external load. So this system is considered as the three-phase four-wire system because we have three phases of power supply and we have one neutral terminal also. Sometimes the neutral terminals are not used. In that case, it can be considered as the three-phase three-wire system. On the other hand, for delta connection, the connection should be such that the starting point of the first coil is joined with the end point of the second coil. That means A1 is connected with B2. Similarly, the starting point of the second coil is connected with the end point of the third coil. So B1 is connected with C2. And similarly, the starting point of the third coil is connected with the end point of the first coil. That is C1 is joined with A2. So in this case, it makes a closed loop. Here the A1 and B2 are joined. Here it is B1 and C2 and here it is C1 and A2. This type of system is considered as a delta connected system. And these three terminals are connected to the external circuit. Here we can see that in delta connected system there is no neutral terminal. So the delta system is always considered as the three-phase three-wire system. Whereas the star connection can be three-phase three wires as well as three-phase four-wire system. The interconnections must be carried out in such a way that if a closed circuits are formed, the sum of the instantaneous EMF in them must be zero in order that there shall be no circulating current in this circuit. It is basically applicable for the delta connected system as the three coils makes a closed loop. Therefore, at any instant, the sum of the three induced EMF should be equal to 0. Otherwise, there may be a circulating current within this loop and this is not desirable. So, thank you.